our seminar, and I'm happy to introduce our today's speaker, Carlos André from University of Lisbon, and he will present talk titled Supercharacters of adjoint groups of radical rings and related subgroups.
Okay, thank you very much for the invitation and the opportunity to speak in this seminar. Well, I decided to do an historical review of the subject on supercharacters. Well, first, one of the applications of, well, I'm not, supercharacters applied in several areas, for example, in the analytic number theory, and you can see some nice pictures that you can find, or the explanation of which you can find in this paper by Garcia, Hyde, and Lutz. And I'm not going to speak about this kind of characters because I'm not an expert on that. No, the definition of a supercharacter, well, this is a theory that extends the usual theory of character theories of finite groups, and we can do it for compact groups also, and we are trying to do it for more general infinite groups, locally compact infinite groups. Well, the subject started with my PhD thesis quite a long time ago, and the notion was formalized by Diaconis and Isaacs in 2008, and the definition is as follows. So we take a finite group and we give a pair of a partition, of certain partition of the group and some characters. And well, the first part of the pair is a set partition of the group, which we call superclass, the superclasses of G, and this defines a character, an orthogonal set of characters that we call the supercharacters, and they have to satisfy three conditions. Well, the conditions were the main theorems of my thesis, and the first one is that the number of superclasses is the number of supercharacters. This is well known for the usual character theory of a finite group. The number of conjugacy classes is equal to the number of irreducible characters. Then every character has to be a superclass function, so it has to take a constant value on each superclass on the first partition. And thirdly, every irreducible character is a constituent of one and only one of the supercharacters that I denote by C. For examples, there are some trivial supercharacter theories. For example, we can take the usual partition into conjugacy classes and the irreducible characters, and this forms a supercharacter theory for any finite group. In another extreme, we can take two characters, the unit character and the regular character, and define the supercharacters to be the set of these two characters. Well, we remove the unit character from the regular character, and we remove the identity from the group G. And this is another supercharacter theory, a trivial one. There is no much interest in this one. A more general construction for supercharacter theory, which appears in number theory, for example. Suppose that we take a group that acts via automorphisms on a given finite group, and then it acts on the conjugacy classes, and we can form, and it acts also on the irreducible characters of the finite group G in the natural way, and then we can show that this is a theorem of Brouwer, a very old theorem, that says that the number of orbits on the set of conjugacy classes is equal to the number of orbits in the set of irreducible characters. So we can take an orbit on the conjugacy classes and make the union over these orbits of all conjugacy classes that are conjugate, say, by the action of A. And then these unions form a partition of the group G, and we can take it as the set of superclasses of a certain supercharacter theory. On the other hand, we also can take an orbit on the set of irreducible characters and in a natural way define the character that is the sum with the multiplicities equal to the degree of the characters that are the irreducible characters that are in the orbit that we choose. And all those sums are the supercharacters of what we want to be the supercharacters. So we have a pair, a partition of G, and a set of supercharacters of G also, and this pair forms a supercharacter theory of G. Well, this is a very nice construction because it appears in several areas of analytic number theory in the study of exponential sums, Gauss sums, and Klosterman sums, and the more basic example is this one, Ramanujan sums, where we take the group, the invertible group of the ring Zn, the usual integers model n, and the natural action on the additive group of the same field, the same ring. Then we can take the divisors of n, and then we obtain a supercharacter series just taking the superclasses to be the set of all integers modulo n, which has a great common divisor with n of that form. And then on the other end, we can take the supercharacters to be the exponential sums, the usual exponential sums for associated with this action. And these are called Ramanujan sums, where there are other sums that appear as a result of constructing supercharacter theories, but I will not go into the details. Just you can find it in the papers by Garcia and others. Now, quite recently, there was someone to find an alternative approach to supercharacter theory, which is based on Schur rings and central Schur rings, and this goes back to Frobenius when he defined the irreducible characters of a finite group. And in this approach, we use something called that we can call the superclass algebra. So we take a subset of a finite group and just define this element on the group algebra over the complex field, the sum of all elements in the subset X. And then we define a Schur ring over G. If there exists some partition, a Schur ring is always associated with this partition of G, satisfying the following properties. So the unit element, the identity, is a member of the partition. Secondly, if we take some member of the partition, that the usual inverse, is also a member of the partition. And thirdly, and this is the more important condition, the sums over the members of the given partition is a linear basis of the subalgebra S. And then we refer to this partition as the Schur partition of G, and denote the Schur ring, the associated Schur ring, by Sk. And we also refer to the basis delta K to be the standard basis of the Schur ring. Well, a central Schur ring is just a Schur ring that is central on is a subalgebra of the group algebra, and it lies in the center. It's a natural definition. Now, this notion goes back to Schur in 33, around 33, and to Violent some years later. And a trivial example is the class algebra, so where the partition is given by the set of conjugacy classes of G. This is the standard example. Now, the relation to supercharacter theories were observed in 2012 by Hendrickson, and he proved the following theorem that reveals to be quite important in the study of supercharacter theories. So there exists a map. We can start with any supercharacter theory of the finite group G, and associate to the partition, to the superclasses, the Schur ring supported by this Schur partition. We can prove that, in fact, the set of superclasses is a Schur partition. It satisfies the three conditions that I gave before, and this correspondence is one-to-one between supercharacter theories and central Schur rings. So this means that if we want to construct some supercharacter theory on a finite group, then we just have to look for central Schur rings over the group. Well, the problem is not so easy. And for example, if you take the G to be the symmetric group, it is not known what supercharacter theory you can define. Well, you can always define the standard one with the irreducible characters. That is quite nice. But others, the problem is open, and it's quite hard to understand. Now, I'm sorry. Now let the G be a finite group, and the S a central subring, Schur ring over G, and the associated Schur partition of S. Then S, we want to construct the supercharacter theory as supercharacters associated with this Schur partition. So we start by using the Wedderburn theorem, and we find some, since this is a commutative algebra, because it is central, there exists some orthogonal idempotents that sum up to the identity of the group. And then since we have a basis of supercharacters, and this forms the set of irreducible characters, the idempotents associated with each one, the set of those form a basis of the center of the group algebra, and we know that there exists some partition such that the given idempotents epsilon I have this form for some subset of the irreducible characters. And then we define a supercharacter to be the associated character to this idempotent. And the usual definition, this character is given by this formula here. And it is clear, since we have orthogonal idempotents, then this set is an orthogonal set of characters with respect to Frobenius scalar product. And we can also prove that this is a supercharacter theory of the group G. So from a Schur ring, and which is defined by the set, the Schur partition K, we can always define a set of characters in this way. And if we go back to the idempotence, then the form of the idempotence is this one here, which is defined in terms of the supercharacters that we just defined there. And this is a way of constructing supercharacters from a Schur partition on some central Schur ring. So it's very standard, and it is not quite new, just standard elements methods. Now, going back to my thesis, when I defined supercharacters, because I want to generalize this for other kind of groups, we now start with a finite field, K. I take the nilpotent algebra consisting of upper triangular matrices n by n with coefficients in K, and define the group, which is just summing the identity matrix to all of those nilpotent matrices. So this is a group. This group, a very well-known group, and we want to define a supercharacter theory for these groups. Well, we start with some upper triangular matrix A, and we can define the superclass just by acting on both sides of A, making the usual product with invertible triangular matrices. So we sum this with identity, and we obtain some subset of the group G. And then we form the set of all those subsets, and this forms a partition of the group G. Is a standard one, is just like equivalence of matrices under unitriangular matrices, as it is well known. Now, when A is the zero matrix, then we obtain the set consisting only on the identity matrix, and it can also be proved that the inverse of some set of these is just the set defined by the symmetric element of the given matrix. So this is almost a Schur partition of G. And in fact, we can prove that this is a central Schur ring over the unitriangular group. Well, the point here is that these sums, the more difficult problem is to know that these sums are closed under product, and this is an element of the group algebra. So we have to prove that given two superclasses or two classes of this form, associated with A and B, we have to prove that the product of those in the group algebra is an element of S in order to have a subalgebra of the center of the group algebra. And to see this, we take the group algebra of the additive group of the given algebra over the finite field. So this is an abelian group, a finite abelian group, and there exists a linear isomorphism with a very simple definition, just subtracting from the basis element of this group algebra the identity, and we obtain an element of the group algebra CA. And then there is a natural action of the direct product of G on the algebra A by multiplying in both sides by the element G and H minus 1. and then we can form this set of fixed points with respect to this action. And this is, of course, a subalgebra of CA. So we already have some subalgebra, the invariant subalgebra with respect to that action. Now, since the group is abelian, the group algebra is always a central Schur ring over A. So the standard basis is A itself. And then the fixed point subgroups is quite easy to prove that it is a central Schur ring over the abelian group A plus with standard basis given by the sums over the elements nu k. So k is a subset of G. We are just taking k minus 1 and then form the sum over all those delta k. And the span of this is precisely what we want, or almost what we want, with respect to the linear isomorphism nu. To see this, we define a new action of G on A. So the first action were given by this product of matrices, and now we are deforming it by the G minus 1 in this other part. And we extend this action by linearity in such a way that we obtain a left CG model with respect to the group algebra of G and not of A. So we are taking just the group algebra of the abelian group and view it as a left CG model. And then, moreover, the nu that we defined and the extension of the map that sends an element of G to G minus 1 in this algebra is an isomorphism of left G models, which satisfies this condition that we want. And therefore, since the product of these two elements satisfies the property that we want, the other one also satisfies because it is an isomorphism. And therefore, we proved that this product is always an element of the given Schur ring of S. So the product of two elements two elements of the standard basis is always a linear combination of the other elements of the standard basis. Now we have defined the superclasses, and now we can apply the usual the general construction to obtain the standard supercharacters. So this is a standard supercharacter theory, and the standard supercharacters also depend on orbits, on G times G orbits, now on the dual group of A plus. Well, and this construction can be made by to compact groups also, if we take the Pontier-Green dual in this instead of A0. Now we have a natural action of G times G on this dual group, the natural depending on the action on A. This is natural, and then we can form the set of G times G orbits on this dual group, and also define the idempotence that corresponds to the usual idempotence associated with each linear character of A, so with each element of A0. And this is a basis of the Schur ring that we defined before, and the elements are all mutually orthogonal idempotents. So in terms of we can now use the isomorphism that we constructed in the proof before, and then we find a linear basis of the Schur ring. And this implies that the set of supercharacters associated with that standard Schur ring over the unitriangular group is just a set of these characters, and they are defined in terms of the orbit of a given theta on the dual group of A by this formula. Well, this is a construction. It is not the first construction of supercharacters, and I will give some more general construction for the case of the unitriangular group. But first, we can ask if it is possible to replace the double action of G on A by the conjugation action and then obtain the irreducible characters. Well, this seems to be a very interesting construction, but it is not expected to obtain nice results, and the problem is that the irreducible characters of the unitriangular group, of a finite unitriangular group, is quite a nightmare. As Diaconis said, it is a well-known nightmare to understand the irreducible characters of the unitriangular group. So we have no good expectation to obtain that. Now, the initial notion of supercharacters was the initial name, original name was basic characters, and I will now describe these basic characters because the construction is quite nice, but a bit technical. And the approach uses algebraic geometry and the definition of some basic algebraic subvarieties that I will skip. I will not do that. So first we choose some entry of the upper triangular matrices, Ij, and we define a subgroup that has zeros to the left of that entry. Well, this is some kind of centralizer for some element that we want. So, but this is just a subgroup, a very large subgroup, and then it is possible to define a linear character of this group just using this formula. So we just look at a given matrix and look at the Ij's position multiplied by some alpha on the field. So this is very elementary to construct, and this defines a linear character of the group algebra, of the additive group of the algebra of nilpotent matrices. And then we can show that it corresponds to one-dimensional model for the group algebra of this group that we construct here with zeros to the left of the column J in row I, to the left of the position Ij. And then we can induce this model to the whole group, and this affords, in this case, it affords an irreducible character, so it is a simple model for the group algebra, and it affords an irreducible character and we call this one an elementary character. In fact, it is a supercharacter by the construction using Schur rings. Now we choose some combinatorial object, a basic subset. So a basic subset is a set of entries that contains at most one entry from each row and each column. And these sets correspond to set partitions of 1 up to n in a very natural way. So the supercharacters will be in one-to-one correspondence with set partitions by this way. And then we define for each of these basic subsets and a given function phi that gives a color to the entry Ij, the color that I call phi Ij, an element of K, which is not 0. And we can do the product of all those irreducible characters. So these characters are irreducible, but the product of them is not necessarily irreducible. There are some combinatorial conditions to assure that this one is irreducible, depending on the set partition associated with D. Well, this character is afforded by a tensor product of those models, of all those induced models that I defined before, and the main result is that there exists, this model is isomorphic to every simple model is isomorphic to a submodel of this tensor product that I defined there for a unique basic set and a unique map. So in a certain sense, we have a partition of the set of irreducible characters indexed by these basic characters and the maps defined on a given one. And moreover, if I take two distinct basic characters, they are orthogonal, and the set, the supercharacters that I defined before are exactly the set consisting of all these those basic characters of UNK. Well, this theorem was the first was the base to the definition of supercharacter theory, because the partition on the supercharacters that I defined here of basic characters satisfies those three conditions for a supercharacter theory. So this theorem motivated the definition of supercharacter theories on any finite group. Well, this depends. Is a certain version of Kirillov method of coadjoint orbits that I will not explain here. And there is a way of obtaining a basic character as an induced character if we take the intersection of the subgroups associated with each entry in the set, in the basic set D. So for each of these entries, we can define this group which has zeros to the left of the position ij, and then intersect all of them, and we obtain this smaller group ud phi. And moreover, we can define also the map just taking the restriction to this subgroup of uij, and then do the product of all those maps. And this is a character of this intersection. And since we have a character and a linear character, we can induce it. And in fact, the basic character or the basic model is the induced model from this subgroup to the group UNK. Now, there are other approaches to other ways of looking at the basic characters. I will not go into details in this part. I just mentioned the formula that we have before in general for these basic characters. So now, quite a long time ago, I proved that what I'm explaining, there exists a bijection between the orbits of this direct product on the dual space, just the multiplication on the left and on the right, and the set of basic characters. Well, this means that by the result coming from Schur rings, that the supercharacter associated with some of these orbits is essentially the same as the supercharacter, as the basic character that we defined associated with the same pair d phi. Well, there is another similar factorization for superclasses that I will skip. It's similar. And now I will discuss this result. Let me show where it is. Well, the composition of a basic character as a tensor product of some elementary characters, and these we know that these models Vij are all simple. So we can ask if in the general situation if it is true that a given model or a given supercharacter is a product as in this as in this as in the definition of basic character, if it is a product of some irreducible characters. So we want to decompose a given character in a general situation as a product of some simple irreducible characters. Well, the answer is almost always no, but we can do something with that. So now we generalize the unitriangular group to this situation. I start with a finite field K as before, and now with a finite dimensional nilpotent K algebra. Well, we can replace K, the field K, by some kind of rings and also A, but I will not take the general situation and look just at this one. And then I formed the group of the adjoint group of this nilpotent K algebra, and look at it as the sum of the identity of a given identity with any element of A. So this is the adjoint group of this ring A. Now the standard superclass is defined in the same way. I just multiply on the left and on the right A by the elements of G, and I obtain a certain partition of the algebra A, and then I sum them with this set with 1 in order to go to the group A, and define the superclasses as in the unitriangular group as the set of all those subsets of G. Now, these are the standard supercharacters. There are other supercharacters, but this we call them the standard supercharacters. And as we did, as I said before, these standard supercharacters come from a central Schur ring, the central Schur ring associated with this partition of G, because we know that K0 contains only the identity, and Ka minus 1 is K minus A, and this is quite easy to show. So the supercharacters can be constructed via the usual construction, and they are parameterized by orbits, double orbits on G on the dual group of this additive group with respect to the natural action. And then we can define also for a given orbit the character by this formula that I showed before in the more general situation. So we have a set of superclasses in this way, very standard ones, and also the set of supercharacters here. And now we can obtain those supercharacters as using the group algebra of A. So A is an abelian group. So this is a group, a central algebra, and with a new action of G on A, so given by deformation by this map, which is just G minus 1. So we deform the product by this part. And we extend it also to the group algebra, to CA, in order to obtain a left CG model associated with this. Now we just take a certain idempotent associated with a character of A, so this theta, we choose one, and we construct the idempotent, and then form the submodel of CA. So we are working on this model now, and we take the cyclic submodel and define it and denote it by V theta. So this is the equivalent of the VD phi's that I defined before. And then this model affords a certain character, and this is affords a standard supercharacter that I denote by this letter. And the set of supercharacters are precisely the set of all those standard supercharacters. So they are afforded by these models here. And we can prove some formulas for these supercharacters, independently of Schur rings. And then this also has a natural structure of a model, left A model, in with respect to this action. So this is not an action of the group, is an action of a ring. So this is a ring with no identity, but we can define the structure of an A model, a left one, in a very natural way in this form. So it also has the structure of a right model if we want, just multiplying theta by A on the right. Now, the point is that, and this is the same as before, in the case of the unitriangular group, this supercharacter is the basic character associated with some d phi, and we have the elementary ones associated with the entries that are in the set D, and we have the supercharacter as this sum. So if we take the theta to be the sum of all those simple ones, so we want the cyclic model associated with each theta I to be the irreducible. In general, they are not irreducible. Then we can decompose the first one as a sum, and we can show, and we did prove that the supercharacter decomposes on a product of these simple ones, just if and only if the model defined by this action, A theta, decomposes into A theta 1 direct sum with A theta t. Well, these summands are incomposable by choice of theta 1. So we can decompose any model of this type into incomposable ones as a left model or as a right model. And the two conditions are equivalent by using the characters. So the point is that we want to prove that, as in the case of the unitriangular group, that these models, these incomposable ones, are irreducible. But in general, they are not irreducible. But this extends the results for the unitriangular group to any algebra group. So in the case of the unitriangular group, as I said, we know that the basic character is a product of elementary ones, and in this case, these characters are irreducible, and they correspond to the direct sum decompositions in this form. So we have an element of the dual space, A0, and we have a model, a submodel, an A submodel, left A submodel generated by this element. And in this case, these are simple models, this and the other one on the right. And we have a composition of the given model as a direct sum of incomposable ones that are in general simple. And they correspond to irreducible characters on the group. unfortunately, we cannot prove that in general the characters that appeared from these submodels are irreducible. In general, they are not. Well, just to finish, we can also extend this for other finite groups of Lie type. I will not enter into details for this, just I want just to give an idea. So here we consider some involution of the algebra and the subgroup of fixed points. We extend this involution. We define an automorphism of G using the standard formula for the automorphism sigma, and then consider the group of fixed points. And these are, if I take G to be the unitriangular group, these groups are precisely the other classical groups of Lie type. And, well, they are P subgroups of the classical finite groups of Lie type. And then we can define also a Schur ring associated with this sigma. I just mentioned the construction. So we start with GG. You can see it as the unitriangular group as a standard example. So we take a superclass of this group and we intersect it with the set of fixed points. So we try to find fixed points on K, and there exists fixed points if and only if the intersection is non-empty. And then we can define the superclasses in this natural way. And these are the superclasses associated with the group, the fixed point subgroup C, G sigma. And well, this is we can prove that this is also, defines also a central Schur ring. And in fact, if it is a central Schur ring, we can, well, it is a central Schur partition, so we obtain a central Schur ring associated over the group of fixed points. And then we can construct well, I will skip this proof. We can construct the supercharacters as we did before, just instead of the homomorphism that sends an element of A to 1 plus A, we have to use the Cayley transform, which is defined by this formula here, and then with some technical methods, we obtained, in fact, a supercharacter theory by using the construction of over the Schur ring. So I will skip this part because it is very technical, and just show that we also obtain a set of supercharacters, and this correspond to very well-known correspondence into finite group between the irreducible characters of a group G, which are fixed by the automorphism sigma, and the set of the irreducible characters of this fixed point subgroup. Well, this is well-known Glauberman correspondence, and we have a characterization of the supercharacters in terms of this correspondence that I will skip. So I think I will finish here, and thank you very much for listening.
Okay, thank you very much for the very, very interesting talk. And so any questions, comments, remarks? So in fact, I have, sorry. Yeah, is it possible to share the slides in the chat so we can study the skipped slides?
Sorry?
Yanis asked, is it possible to share the slides in the chat so we can study the skipped slides?
Yeah, I think that I can. But, how can I do that? I will.
That would be great.
How do I do that? I don't know. To share on the chat.
Yeah, you can just put them.
I just
drag and drop. Yeah.
drop it to the chat
To the
symbol.
chat, yes, here in Zoom, I mean.
Yeah, let me try to find them.
Yeah, because a lot of slides was skipped and it's really extremely interesting. So I would like to study.
I think that they. Oops. Oh, I don't know what I did.
Probably you can send them to Jabir and he will put them.
It may be better to do that because
Yeah.
I'm
Okay, probably you
let
can.
me see.
Okay, if it's not possible now,
I cannot do that.
okay. So probably could you possibly send them to Jabir and he will put them.
Let me try it again.
We put it
I
on
did
the
it.
side.
I did it.
This slide, we put it on the side, our European seminar site.
Yeah. So
Oh, great,
I
thanks. Well, we have slides here now. Okay, great.
okay.
Well, other questions or remarks, comments? Well, I have 100 of questions because I've cited your works a lot. But let me ask just one question.
Yeah.
As I realize, your method allows to classify all irreducible characters of the maximal unipotent subgroup of a finite group of type Cn of maximum degree. Yes.
Yes. Yes. That's true.
Yes. And
Of
well,
maximal degree.
yeah, maximal degree, yes.
Yeah.
Well, now me and my students we're trying to classify all characters of sub-maximal degree for classical groups. And is it true that for Bn and Dn, your stratification doesn't give an answer for maximal degree? I mean,
In terms of supercharacters,
yeah, in terms of character, yeah.
yeah.
So as I realize,
I think that it can be possible.
well,
For type Bn and Dn.
yeah. So in your paper with Anna Neto,
Yes.
we have just that the result that the character of maximal degree is just a constituent of your supercharacter, but not
Yeah.
exactly the supercharacter.
Yes, that's true. That they are not
Okay.
exactly the supercharacter
Well,
in other cases.
may I
Because
address a lot of other questions to you by email?
okay,
Okay, thank you so
you're
much.
welcome. Okay.
Any other questions or comments or remarks? Okay, if not, then let's thank the speaker for this was really nice talk. So I've learned a lot of new facts and concepts from this.
Thank you
Thank
very
you very
much.
much.
Thank you.
Okay, so that's all.
Okay, that's all. See you next week.
Okay, see you.
See
Bye.
you. Bye.